Thank you very much for inviting me to this AMLD 2021. And today's topic is AI and sustainable energy. But why would we need AI for sustainable energy? Like in many other engineering fields, one answer is system identification, or in other words, the estimation of parameters of a mathematical model of the power grid in our case. Why would we need those parameters? With the rise of renewable energies, many distributed energy sources have been installed on distribution grids. And these sources need to be controlled. And the controller controlling them needs those parameters to be tuned optimally. There are other motivations like load prediction or sensitivity analysis, but this is an entire field in power systems that I will not go more in depth. In this presentation, I will define what is power grid identification, and then I will present Bayesian methods for it. So to define power grid identification, I first need to define what is a power grid. For us, it's a graph of n nodes linked by edges. Each node represents a load, a generator, or both, or a subgrid. The interaction between those nodes and the flow of current in the power grid is defined by the very known Ohm's law and Kirchhoff's law. Now, Kirchhoff's law is an unweighted sum of currents. So for the rest of the presentation, I will put the resistance in Ohm's law on the voltage side and use conductances instead of resistances. And since many power grids are in alternating current, we need to use complex values. So this conductance becomes an admittance, which is written here, Yij. Each line have its own admittance. For example, the line from node 2 to node 3 has the admittance Y23. Why do we need complex numbers? Because an alternating current signal is a sinusoid, and it's characterized by a magnitude and a phase. So we need two quantities. Now, to model the entire network, we need to work in matrix form, which all those laws become the equation I equals Vy, where Y is a complex matrix of n by n elements. We will call this the admittance matrix, and this is our target for identification. So we want to know what it is. As you saw on the first slide, distribution grids can be quite messy. Let's say there's connections a bit everywhere, added all the time because of new households or new constructions. So it is not well known compared to transmission grids that are monitored everywhere, that we know their admittance metrics fairly well because the stakes are higher. However, with the rise of renewable energies, for voltage stability, energy distribution companies had to install many sensors to monitor distribution grids. So we have access to more and more data on those grids. So we could use this data to identify the admittance metrics. Trivially, one could say, well, we can take n samples, we invert the voltage metrics, and we should get Y, right? Mathematically, it works, but in practice, there's a dichotomy between the stability of the grid. Essentially, you want nothing to happen on that grid. You want the voltage to stay very constant at the rated level, like 220 volts, for example. And it's opposed to identification, which typically need excitation of the system, which means you need a high magnitude of signal. So in order to cope with the singularity of this voltage matrix, you could say we take the pseudo inverse, which is also called the least squares. And we take a large number of samples, and we should get a good estimate. Problem is we have noise on both V and both I from the measurement. And even if it's small, and even if you have an infinite amount of samples, this will lead to a bias of your estimate. We then go for maximum likelihood estimation, or MLE. This estimates at the same time the parameters, the Y metrics, the noise, which is delta I for the current and delta V for the voltages. Graphically, if the vertical axis is the current and the horizontal axis is the voltages, the least squares would minimize the vertical distance to a regression line, and the maximum likelihood minimizes the orthogonal distance. So it is more sensitive to lower signal and less sensitive to noise. Our noise is time dependent. It depends on the voltage of the grid and the current. So we need to use weighted norms that are represented by the quadratic form down below. They are weighted in the final log likelihood by the covariance matrix of the noise. Now, this is a frequentist approach. It learns by itself, works by itself, doesn't need any input besides the one given by the sensors. In machine learning, many people consider these kind of self-learning approach better, but we realized realistic experiments with realistic noise levels, loads, parameters, and this estimate is not very good. You can see an image of it on the top left. Why can I say that it's not very good, or any other practitioner in power systems? It is because power systems have been studied for decades, and we have a lot of information a priori on admittance matrices in general or a particular system. To make use of this prior information, the most common framework is Bayesian estimation, which essentially allows you to enhance your estimation using the Bayes rule, which shows at the bottom left. If A are the parameters and B are the state that you're measuring, then you do not have a prior on the state. So you can input a non-informative prior, which is essentially a constant. So when you try to maximize the likelihood, it will be simply canceled. So we are trying to maximize the posterior likelihood shown up to the right, or it's negative, with the prior P of Y. So it's logarithm in the log space. The optimization problem is more robust and you can drive it where you want. The problem is if you are wrong, you can create a bias. So the most simple prior is when you already know some parts of your grid or the entire one, you can add these measurements that you have done already in the prior, and it will drive the estimate towards these measurements. It allows for some tolerance, like the uncertainty of your measuring device. So the data can essentially still drive it away if it's wrong. Another very common prior is sparsity. It is the belief that every element of the admittance matrix has a high probability of being zero, which would correspond to a line not existing. This prior, if you believe too strongly in it, is straight out wrong because it considers that every entry of the admittance matrix is zero. So in order to make the admittance matrix sparse enough, you can create a very large bias. To counteract this bias, we came up with a contrast prior, which is a sparsity added to a prior on the sum of the elements of the admittance matrix. So if you at the same time believe that the elements are zero, but that their sum is large and non-zero, which is represented by this quantity gamma, then you end up with a solution in the middle. We will use this in the simulation that we conducted with maximum likelihood, and I will show the results a bit later. First, I want to talk about a couple other priors that are common to distribution grids, like a constant resistance over inductance ratio, which typically means that you use the same type of cable everywhere on your network, or a prior on the sign, because the resistance is always positive and the lines are mainly inductive, so their reactance is negative. As distribution, I've talked about the center of these distributions, but not about the distribution themselves yet. We use a Laplace distribution, which in the log space become a L1 norm. It's fairly standard in statistics. You can also use quotient distribution, also fairly standard. This would result in an L2 norm or other kinds of distributions. Now, I've already showed you the results for a maximum likelihood. If we use the contrast prior with the same settings and using a data-driven estimate of the quantity gamma that showed us up in this prior, then it yields the maximum a posteriori estimate, which shows in the center of the screen. Now you can see this matrix is a lot more sparse. The white parts are the zero elements. And if you compare it to the exact admittance matrix, it looks very good. The error is a little bit above 10% with less than 1% on the zero elements, which means we achieve a good estimate of the topology. And we can compare this to other standard methods like least squares and lasso, which essentially estimate a zero admittance matrix. So I have a 100% error. But this a posteriori estimate is not trivial to find. The log likelihood has a complex analytic form, which is bilinear due to the multiplication of delta V and Y. So we need to use an iterative method, which is the alternate descent, consists of fixing Y as a constant and optimizing for delta V, and then fixing delta V as a constant and optimizing for Y, and so on and so forth until convergence. But the Y sub problem is also quite complex as it is non-smooth. So we use the smoothened approximation of the L1 norm as an L2 norm weighed by the result of the previous iteration. This makes both subproblems quadratic and makes the optimization problem much faster to solve. In fact, it's 10 times faster for our case as a commercial optimization package, and it can also handle all priors, including the contrast prior, which may not be convex. To conclude, we performed the maximum likelihood estimation in realistic conditions with measures of voltage and currents on every node of the grid and fairly low but realistic noise. The estimate was not very good because of the lack of signal in the estimation problem, and especially for the high admittances, which corresponds to short lines or switches, and the nodes where loads are low, because the signal is even lower on these nodes. We realized that we could take advantage of a wide variety of known information to improve this, this estimation. And we did this on the same realistic simulation that can serve also as a benchmark for future methods or to compare to past methods. But to do so, we had to develop a new optimization algorithm because the problem is very complex. Do you have any questions?
Thank you very much, Jean-Sebastien. This was a very nice introduction to the topic. I mean, some hints to very deep math, but not too deep, not to be understood. Sorry. So, questions from the audience? Not yet, so I will start myself. With this one, this conference is called Applied Machine Learning Days. Pure research is great, but applications is what really interests us. So how much research do you think it is still needed before taking these concepts out of the EPFL and straight on a real smart grid or a real distribution grid?
So I'll not go too much in detail into the roadmap, but the first target is to make the identification tool that we developed using this method for tri-phased network, because most networks in applications are with 3 phases. This is mainly a development job. And then the other one is lifting the assumption that you have information on the voltage or the state of every node. Because in practice, many grids do not have sensors everywhere. This can be done through a variety of methods. The problem is that the signal is generally very low. It depends a lot on the grid and on the load profiles and a variety of factors. But I think it can be done. It should be done, let's say, in the next year. And then it would be ready. It's not a controller or something with a direct impact on the state of the grid. So it's safer to try in a real setting. So it shouldn't be too much research before it can be applied.
Understood. Maybe we can take inspiration from the content of the previous talk for some hint about how to include hidden nodes in the network.
Yes.
That's the power of these kind of conferences. So questions are starting to come in the Q&A tab. Don't be shy. So there is one from Braulio. Can you elaborate on the realistic scenario of your study?
So we assume that the grid is monitored by micro PMUs, which are the next PMUs, sorry, synchrophaser measurement. So it's devices that are made to measure the phase and the amplitude of a sinusoid. It's the sensors that are the most widely used in power grids. And micro PMUs are made for lower power requirements, lower voltage, and they were developed for distribution grids instead of transmission grids. And they have a better accuracy than PMUs. And typically we took the specification of several of them and tried to see what is the standard noise level. And we use this together with load profiles generated by realistic load profile generators published by another university. And with these data, we took the 1, 2, 3 bus network from IEEE Explore, which is a standard benchmark, and simulated it and tried to identify the admittance metrics back.
Yeah, thank you very much, GS. There is another question which is very interesting. So Sylvain is asking, you mentioned that Lasso completely fails in the task, even though the maximum a posteriori estimate with the Laplace prior works. And Lasso should not be that different from the maximum a posteriori estimate. Well, I would say not really, it is quite different, but I leave the answer to you. So why Lasso fails and the maximum a posteriori works?
The answer is the error on the voltages. Lasso is a maximum a posteriori estimate if you have error only on the left-hand side variable, which is the current in our case. But if you also have error in the right-hand side variables, which is the voltage here, a bias appears on your Lasso estimate. And in our case, since the error on the voltage is very large and it's multiplied by very large parameters, typically you want your resistance of the lines to be very small, so its conductance is going to be in the tenth of thousands of inverse ohms. So this bias becomes very, very large. And in the case of ordinary least squares or Lasso, it means that the estimator cannot find any correlation between right and left-hand side variables, which means essentially that you get a zero matrix.
Yeah, correct. If I may add something to this answer myself, the problem with the error on voltage, with the noise on voltage, is that it is very small in absolute terms because micro PMUs are quite extraordinary devices, but in terms of signal to noise ratio, it's not negligible. I mean, the variation in the voltage are so small that even a small noise is relevant. And this is why considering the noise also on voltage is critical in this kind of applications.
Yes, I often compare our problem to face recognition at 300 meters in the night in the middle of a blizzard. It's kind of hard. You do not have much signal strength.
Nice metaphor. One last question, and you have 1 minute to answer. I don't want to start a war of religion about frequentist approach and Bayesian approaches, but you talked about Bayesian estimation and you did not show a full posterior distribution of the parameters we would like to estimate. So do you think that the estimation of the full posterior is feasible? It is useful? What are your thoughts about that?
So it is actually, compared to other posteriors and other problems, it is not a very complicated posterior distribution. It's basically the product of a Gaussian and a Laplace distribution. It still has a very long expression, which doesn't have its place on slides. But we managed to extract the Fisher information and error covariance out of this posterior. So it is very useful. And yes, we computed it.